Hello, welcome to our lecture video for section 2.4, Interpretations of the Derivative. Just a reminder about what I mean and what the textbook means when we talk about interpretations. This means some way of taking a mathematical statement or a number and saying, what does that tell you about the real world context of the problem? So for example, with this warm-up, s of t here is a function that outputs your distance in miles from home, t minutes after you started driving to school. So when I say interpret each result, it means like, what does this statement say about driving to school and your distance or your speed or time or whatever. And for part C, here you're going to just use these facts, A and B, to see if you can estimate this one. Using what you know about linear functions, you can pretend that s of t is approximately linear to help you estimate that. So that's my hint. Give it a shot. I'll show you the answers in 3, 2, 1. And here are some answers for this. So for the first one, A, when we say s of 5 is equal to 1.3, the input is the t minutes, so that number 5 is the number of minutes after leaving, and the output, s of t, is your distance from home. So this just means 5 minutes after leaving, I was 1.3 miles from home. S prime of t, let's remember what this represents. It represents your speed, which we talked about in section in 2.1 and 2.2, but I just want to remember what the real definition of s prime of 5 is. It's the limit as h approaches 0 of s of 5 plus h minus s of 5 divided by h. And I want to think a little bit about units here, because thinking about units of numbers will help us understand stuff in this section a lot better. So the units of s of 5 plus h minus s of 5, that's a change in your distance from home. So the units of this is miles in the top, and the units of h represents input into the function. So you have a number of miles in the top, and the input into the function is minutes. So h represents a change in the number of minutes. So when you get a smaller and smaller change in the number of miles with a corresponding small change in the number of minutes, and you divide them, you get miles per minute. So that's why this means 5 minutes after leaving, my instantaneous velocity was 0.5 miles per minute. With a period there. Okay, now C is based on the assumption that 0.2 minutes is not very long. We're just going to assume that you're going at approximately the same speed. You keep going about 0.5 miles per minute over this little 0.2 minutes. That might not really be true, but if this is a pretty small interval from like 5 minutes to 0.2 minutes, then that part of the function might be approximately linear. So you might be able to make a good guess. We don't really know that. I mean, they might have just stopped immediately after this and didn't really go any farther at all. But let's just say you go about the same speed. So you want to get the equation of a line with that slope. Remember, the slope is equal to the slope of the derivative is equal to the slope of the function at that point, and with that xy point. So just using point slope form, you get this result here. Y equals the starting y plus the slope times the change in x. And I want to think about what the units of this is here again, because thinking about units will help us understand what this is all about. So when you do it this way, you're saying 1.3 miles, that's like the starting distance from home. What if you were at x equals 5. So if you plug in x equals 5 into this, you just get 1.3. So that's like the starting distance. And then the 0.5 is miles per minute. So it's 0.5 miles per minute. And then the x minus 0.5 that we have here, well, that is actually, maybe I should move this down here, that x minus 5, when you plug in 5.2, is actually equal to 0.2. So we're doing this 0.5 miles per minute times 0.2. What does that number 0.2 represent? Well, it represents 5.2 minutes minus 5 minutes, so it's a change in the number of minutes. So it really means 0.2 minutes, which is like 12 seconds. So if you're going 0.5 miles every minute for 0.2 minutes, then you can really think of the units as canceling out here. You get a number of miles. So that's why this result here means 1.3 miles plus 0.01 miles. As you can think of the units as canceling out, which is basically what really happens. Miles per minute times the number of minutes gives you the distance that you go. We're essentially doing rate times time equals the distance traveled in that 0.2 minutes. So that gives you 0.0. Did I multiply that wrong? This is supposed to be, this is the wrong answer. Whoops. 0.1, 0.5 times 0.2 is 0.1, not 0.01. So it should actually be 1.4 miles from home. And that's that. Let's go on to do some more examples where the main ideas with all of these is thinking about units and thinking about what the derivative tells you in terms of a rate of change and how you can use that rate of change to find the actual change in y. So still, we're going to be using the same sort of concepts that we talked about in bonus section 0, where slope is delta y over delta x, and if you want to find a corresponding change in y, if you know delta x and you know m, then that delta y is whatever your delta x times m is, and how you use that to find new values of y in different kinds of contexts. So first, we're going to introduce some notation that will help us think about derivatives and what derivatives mean in general for different kinds of functions. So there's this alternate notation which I think is really helpful for understanding what a lot of things in calculus really mean. It's called Leibniz notation, not Leibniz, Leibniz. He's a German guy named after Gottfried Leibniz, who was one of the inventors of calculus. He's an interesting guy. Did some interesting science stuff. The other inventor of calculus is Isaac Newton, who is a little bit more famous because he did a little bit more stuff. Except, I don't know, I think Leibniz is a pretty interesting guy. You can read about him on Wikipedia if you want. Anyways, so it's another way of talking about the derivative, and you also use this notation for integrals later on. So if y is the output variable, so like you have the y-axis and the x-axis, then f prime of x can be written like this, dy over dx. And let's talk about why it makes sense to write things like that, and why it's useful for understanding derivatives. So first of all, let's remember what an average rate of change is between 2 points. You can think of this as a, we call f of x plus h minus f of x divided by h. So, and we think of this as like a delta y divided by a delta x, because the top of the fraction represents a change between two y coordinates, and the bottom represents the corresponding change in the x coordinates. And that represents the slope between 2 points on the graph. Okay, and then the instantaneous rate of change, and the instantaneous rate of change has this formula. I just paused it for a second because I was having some computer trouble. But this is the definition of the derivative we had. And the way you want to think about this is remember that h represents the delta x, the change in x between 2 points. So as that gets smaller and smaller, we could write this another way. We could call this, the limit as delta x approaches 0, and write the top of this as the delta y that corresponds with that delta x. So just replacing the h with delta x, and that's what the derivative is. It's the limit as the vertical change and the horizontal change between 2 points progressively get smaller and smaller towards 0, and you get the slope of the tangent line. So it still represents the slope, but it's not between 2 specific points. So the notation is to say that the delta y is essentially the same as dy, and the delta x, as it gets smaller and smaller, you call that dx. So that's why dy represents a very small change in y, and the dx is the corresponding very small change in x. And this is worthwhile because it tells you that if you have the average rate of change between 2 points, so like if the delta x is small, like close to 0, then this average rate of change is approximately equal to the instantaneous rate of change. So what you can do is you can say delta y over delta x, the actual slope between 2 points, is approximately the same as dy over dx. And this is the same thing as, and this also helps you think about units, because what is the units of the derivative? It's whatever the units of y are divided by whatever the units of x are. And that's going to represent some kind of rate of change in some context, and we'll look at some of those. And this also means that if you know this slope at a point, and you want to estimate what the change in y is, you can multiply that by the change in x. So in other words, delta y is approximately this dy over dx multiplied by the corresponding delta x. And another way to say this same thing is to see what is a approximate change in y. It's approximately f prime of x at that point times your delta x, because f prime and dy over dx mean the same thing. So this is a main thing that derivatives are used for, is to estimate the change in an output. This is kind of like what we did with the warm-up problem. And let's look at some examples of how we can use this concept to figure out what the derivative means. So here's a good example you should try to do. So this function f tells you the cost, the output is the cost, C, of extracting T tons of copper ore from a mine. So this is useful in case you're ever running a copper mine or running any other kind of business where you have some kind of cost function like this. So part A, write a sentence about what the numbers 2,000 and 100 have to do with the copper mine. And part B is maybe slightly trickier. Try to estimate this. And now is the time to pause it, because the answers will appear in 3, 2, 1. And here are the answers. So for part A, when the input into the function is 2,000, that means we're talking about when extracting 2,000 tons. So you could say after extracting 2,000 tons or when extracting 2,000 tons. The cost is increasing, the cost increases at a rate of $100 per ton. And I know the units of this are dollars per ton because this represents a small change in the cost divided by a small change in the tonnage. So the units of cost are dollars, the units of the weight is tons, so you get dollars per tons. So that's how fast the cost is increasing. So you can expect that extracting the 2001st ton is going to cost $100 more than the previous 2000 tons. So it's the rate that it costs to mine extra copper. And for part B, the trick is to recognize that f of 2005 minus f of 2000 represents a change in y in the function. So if you want to find a change in y, we can use our old fact that a change in y is equal to a change in x times the slope if it's a linear function. And if we're just estimating it, we kind of have to assume it's approximately linear if we're trying to estimate it, that the rate of change is about $100 per ton for around this interval of tons. So, and again, it might be changing. This function might be curved downwards, in which case it's getting cheaper to mine more, or maybe it gets more expensive to mine every additional ton after this, but we don't really know what the shape is like. So our best guess is that it's about linear. And so, okay. I just wanted to jump in here from the future in the middle of my previous explanation to explain that fact I just said in a little bit more detail. Why is it okay to assume that it's about linear for values near 2000? So I just made up a function about 0.03x squared here, might be this cost function. It has the same point, f of 2000, this is black curved one here, is a parabola. F of 2000 in this case is equal to 100,000, and f prime of 2000 is 100. That's actually the slope of the point there. And so what you can see is, as long as you have a regular old smooth function, as long as you're talking about values of x really close to 2000, there isn't much difference between the black curve and the red curve here. And if you zoom in, you can see there it really does get to be pretty, they're almost exactly the same. So if we zoom in this much, you can't even see the difference between them. So 2005 tons is here, and the change in the cost between producing 2000 tons, which is 100,000 here, and 2005 tons, that difference is going to be almost exactly the same whether or not you use the actual parabola, the actual cost function I made up, or the tangent line. Now that doesn't work very well if you're talking about values of x that are very far away. So like if I was using 2200, so like that's a change in x of 200, then you can start to see there's a real difference between the parabola and the linear approximation. But most functions are pretty close to lines as you zoom in close enough to them. And of course, how close you have to zoom in to make it look like a line depends on the function, and depends on the value of x that you're talking about. But the general principle is always the same for all functions. So that's why it's okay, like when you look at this notation here, the dy over dx, that represents the slope of the red tangent line here, but the delta y over delta x, that represents the difference in the, like the slope of the secant line, and between x equals 2000 and x equals 2005, and for values of x that are really close to 2000, there isn't really any difference here. So that's why we can say that this is approximately true. Okay, so I'll let you continue hearing the rest of my explanation that I interrupted. The rate of change, the dy over dx at that point, is $100 per ton. That's approximately the average rate of change between 2 points near there. So that f of 2005 minus f of 2000 is that change in y, which corresponds to this change in x of 5. And now, to understand what all this really means, it always helps to think about units in this section and throughout calculus, but especially here, that 5 is a number of tons. It's an increase in the number of tons. So if you multiply both sides of this equation by 5 tons, you do $100 per ton times 5 tons, gives you a result of $500, which is how much more it costs to mine 2005 tons than mining 2000 tons. So it's like the additional cost for those 5 tons of copper ore. Or you could think of it as the marginal cost in economics terms. So that sounds good. We'll do a couple more examples like this. That'll be maybe a little trickier than this, and then a practice problem or two at the end. Here are a couple more problems. So f of x represents the elevation in feet of the Mississippi River, x miles from its source. What are the units of f prime of x? So is it miles or feet or whatever? And what can you say about the sign of f prime of x? Is f prime positive or negative, or no idea? And then here, W is an invertible function which gives you how many gallons of water an oak tree of height h feet uses on a summer day. So try to write out what these different quantities would mean. And we will make the answers appear in a few moments. So let's pause it, and the answers will show up in 3, 2, 1. And here are the answers. So for example 2, the units of f prime of x are feet per mile. So this represents, f prime of x represents the rate that the elevation is changing as x increases. So the units of y are feet here, and the units of x are miles. So a change in feet divided by change in miles gives you a rate of change in feet per mile. So this represents basically the slope of the river itself. Like, at what rate is it going downhill? So like if you go 1 mile away from the source, how does the number of feet change? So that's why you'd expect the sign of f prime of x to be negative at all points, because rivers go downhill, always. So meaning an increase in x moving away from the source of the river, away from the spring and towards the ocean, results in lower elevation. If it were true otherwise, then the river wouldn't go that way. You'd have a lake if you were going uphill, but then the elevation of the surface would still be the same, because water never ever goes uphill. So anyways, example 3 is also about water, sort of, but first of all, W of 50, the output of this function, is the volume of water in gallons that a 50-foot tall oak tree uses on a hot summer day. So remember, W inverse, like if you have, let's remember what the inverse function does. W of h, if that's equal to y, so y is the number of gallons and h is the height, then what W inverse does is it switches the number of gallons and the input with the output. So instead you input a number of gallons and the output is the height. So that's what inverse functions do, is they swap those two things. So when you see an input into this one, into an inverse function, that really represents the same thing as the output of W did. So that represents 40 is a value of y, or in other words, a value of the output of the function, which is gallons of water. So this result, W inverse of 40, is the height of a tree that uses 40 gallons of water. So the output is the height, and the input is the volume of water that the tree uses on a hot summer day. And C is asking about W prime. So W prime represents a rate of change if we think of this as like dy over dh, so it represents a rate of change in the water usage as the h increases. So as the tree goes taller, that's why this is 3 gallons per foot. So if the tree grows 1 foot taller, like up to 6 feet, you can estimate that it's going to use 3 more gallons of water. So it's not the rate like per day that it's using the water, it's the rate that its water usage per day increases per foot of the tree growing taller. Next up, some practice problems. Here are these practice problems. The first one is just writing out an interpretation about what f prime of a tells you with a sentence, include units. The second one, I should mention this notation might be slightly different. I didn't do it with this vertical bar here before, but if we say that v is a function, is the output value for a function of r, what we said before was that dv over dr represents f prime of r in general. But if you have this vertical bar with r equals 2, that just is giving you a specific value of r. So saying dv over dr with r equal to 2, that's just another way of saying f prime of 2. So that's what that means. I'll let you try these, so let's pause it, and the answers will appear in 3, 2, 1, and here are the answers. So first of all, f prime of a is the rate of change of c with respect to a. In other words, the rate that the cost increases as the size of the house increases, and the units of this is f prime of a represents a very small change in the cost divided by a corresponding small change in the area. So that's dollars divided by feet squared. So the units are dollars per square foot. So that's what that quantity means. Let's look at number 2 here. So first of all, for small values of delta r, meaning if r is near 2, that means delta r is small, then we can assume that if r is close enough to 2, then the graph looks kind of like a line there, or it's not too bendy, it's kind of linear. So the slope we can assume is approximately 16, around there. So in order to get a change in v, you just multiply that slope by the corresponding change in r. So yeah, the change in the output is approximately the slope at that point times the change in the input. And for part B here, let's see, this is just giving us a specific value of delta r, so you just do that slope times 0.1 to get 1.6. And with part C, the only difference is it's giving you a starting v coordinate, and if r is 2.1, that means delta r is 0.1. So this is still the starting v coordinate plus the slope times the change in r, and that ends up giving you 33.6. And so that is basically what this section is about. Knowing what a dy over dx represents for a particular y or x, and also using that to estimate like a small change in the output that corresponds with a small change in the input, and what that tells you about the situation. So I'll see you in class.